All right, ladies and gentlemen, welcome to your very first video for Algebra 2. We're going to be looking and starting in Chapter 2, looking at relations and functions to begin with. And what we want to do is we want to figure out what they are and what they look like. So to start off, we want to look at what is a relation. Pretty much everything is a relation. So a relation is really just a set of ordered pairs set of pairs of inputs and outputs, or input values and output values. Values just being numbers or anything that we can look at. Okay, so in this case, we really kind of look at the set of ordered pairs. Now, this is a set of ordered pairs. The squiggle brackets here represent the fact that we have a set. And then the ordered pairs are these groups of coordinates, as you have seen in the past. So this has four things, four items in our set, and each of these items have a coordinate. In the real world, this can represent data such as, I don't know, heights of people compared to shoe size, or something along that line. It would be a relation to compare height to shoe size, or age to shoe size. And like I said, pretty much everything in math, or a lot of the stuff in the world that you compare, can be called a relation. So in what we have, one of the things that we do in this is we look at, okay, what is the domain of this particular relation? And the domain is the set of all inputs. And in the world of algebra, for the most part, our domain is the x coordinates. Now, sometimes we use different letters in different equations later on, but for us, this is a coordinate. So this is the x coordinate, the y coordinate. So the domain is a set of all inputs, and if we look at this, we have a domain. We can look at all of my x values. The domain would be 1, 2, 3, and 2. But since we have the 2 is repeated, we don't have to write it again. So we would say the domain is the set of values 1, 2, and 3. All right, so if the domain is the set of all inputs, we say the range is the set of all output values. And again, in the world of algebra, for the most part, we use the letter y. So the y coordinates up here, if you looked at that, the y coordinates would create the range set of 6, 7, and 9. Notice I use the squiggle brackets because it's a set, right? It's a set of all values. Okay. And the last thing I want to talk about is what's called a mapping diagram, or last thing on this page. And a mapping diagram is something that shows really kind of what goes on between the x's and the y's. So we could say we have a box for x values and a box for y values. I would say, okay, our x values in this particular relation are the values 1, 2, and 3, and our y values are the values 6, 7, and 9. And then what the mapping diagram does is it maps each of the domain values onto the range values. So 1, we know, maps onto 7. So 1 maps onto 7, and that's actually one of the things we say in math. We say something maps onto something else. So 1 maps onto 7. 2, you notice, maps onto 9, and it maps onto 6. And then 3 maps onto 7. And that would be a mapping diagram for this particular relation. So we would be mapping domain values on to range values. All right, and then what we do in math is we say, okay, well, relations are all good, but what we like to look at when we get into the bigger level math, we want to look at what's called a function. Oops. A function is a much more specific thing. It starts as a relation, but each domain value has to be paired with one range value. And it can only be matched with one range value. It's not allowed two separate range values. So the mapping diagram, an x value can only be mapped to one y value. So this is an example right here of a function. Now, it's automatically a relation because it is a set of ordered pairs. But what makes it a function is the fact that 1 only maps to 3, 2 only maps to 4, 3 only maps to 6, and 4 only maps to 9. And what you may notice is from the previous example, this is not a function because 2 maps to 9 and it mapped to 6. And if you were to think about that mapping diagram where we had the value 2, it mapped to two separate values. So if you're looking at a mapping diagram, when you have two arrows coming from the same x value, that shows that it's not a function. All right, let's move forward here. So this is a function. And when we start looking at functions, we like to start looking at graphs. And not all graphs are functions. But what we can do is we can do what's called a vertical line test to determine if the graph is one of a function. So if we were to do something like this and just had a bunch of dots right here, these dots represent ordered pairs. And what we would do is we would take a vertical line, okay, and each of these vertical lines only touch, now these don't actually exist, right? They should really just be dashed lines. So let's try that again. The lines are just to test, does the vertical line only touch the graph once, or does it only touch one red dot in this case? And the answer would be yes. So this is a function. Let's see what else would a function be. Let's go with, if we were to do something like this. Some of us might remember that this is a parabola. This is graphed from a quadratic equation. But what we want to do now is we want to say, okay, well, is it a function? And we take this vertical line, and this vertical line only touches the blue line once. Each of these only touch the blue line once at these little intersection points here. And again, because it only touches once, each of these vertical lines, this is a function. So what would a non-function look like? Well, a non-function would look a little bit something like this. If we were to graph what's called an ellipse. Now, ellipses have equations, but ellipses are non-functions, and here's the reason why. If I was to take this dashed vertical line, do a little test, well, it touches the red line here and here, and because it touches more than once, this is a no. This is not a function. All right. Function notation is super important in the world of math. Function notation is kind of our higher level way of talking about equations, but specifically talking about the equations actually being functions. Function notation looks like this. This is super, super important. A lot of people believe that this parentheses means multiplication. That's not it at all. This is read f of x. And essentially what that means is we're talking about a function, and we're going to call that function f. Sometimes we could do things like this. We could call a function g. We could call a function h. We could call a function m, whatever we want to call it. In this particular case, this is our most common one, I would say. We're talking about a function f, and the variable that's in the equation is x. Now, we could do something like this. So that's why I left this as h. We could say h of m. Now, this would mean that h is my function, but m is my variable. Please do not believe that that is multiplication. That is not multiplication. So what can we do with the things that we just learned? Well, there's a lot of stuff that we're going to be doing. So one of the first things we're going to be doing is really just, you're going to be answering questions such as, what is the domain? What is the range? And is it a function? And so we could look at a set of ordered pairs like this. And we could say, okay, well, our domain, pretty easy. Remember, domain should be the easy one. It's the set of numbers that represent x values in this case. And we're going to say 1, 2, and 3, it looks like. And our range is, let's see, we have 3, 4, 5, and 8. So we have 4 in here. 3, 4, 5, and 8. And then we need to ask ourselves, is this a function? And there's different ways you could do this. One, for the most part, you guys are all going to be able to look at this and determine if this is a function. But let's just go ahead and do a mapping diagram to just practice that as well. We have our x and we have our y. Our x values are 1, 2, and 3. And then we have 3, 4, 5, and 8. 1 maps onto 3. 2 maps onto 5 and 8. And then 3 maps onto the 4. Now, a mapping diagram is not necessary, but I just wanted to practice that skill one more time. If we notice that right here, because 2 maps onto both 5 and 8, this is a non-function. So this is a non-function. All right. What else can we do? What else can we do? Oh, let's actually backtrack one here. We could look at graphs. If we were to look at a graph of a function, or of a relation to determine if it's a function, we could say something along this line. Let's backtrack. Let's call this a blue line now. And let's call that number a 7. There's a very specific reason I want to look at this particular graph. Because I want to determine domain, range, and is it a function? Well, we already realized earlier that this is a function using the vertical line test. So what would be our domain? Well, it's not going to be a list of numbers because there's infinitely many. In this particular case, there's x values. This arrow means it goes always to the right and always to the left, which means the domain is all numbers. And what we say is we say all real numbers. We'll get to imaginaries later in this class, but all real numbers. And the shorthand for this would be a double bar R. And that would be math shorthand for all real numbers. But what about the range? Again, I'm not going to write a list of all of these numbers because it includes 7, 7.1, 7.2, 7.39, all those. I don't really want those. But it does say it starts at 7 and always goes up. So what we want to say is, what are the y values? The y values are 7 and bigger, and we can actually use an inequality to show that y is greater than or equal to 7, and that would be our range. Again, we're using the set notation, the little squiggle brackets, to show that it's a set. All right, our last piece here is going to be using function notation to evaluate. So this function notation represents a function, and the function is represented as 3x minus 1. And what we want to do is we want to do an evaluation. That is not a negative sign. Sorry, that's bad. That's just a indentation sign. What I want to do is what's called f of 2. F of 2 says, let's replace the x with a 2. So f of 2 would be 3 times 2, because originally it's 3 times x minus 1. And if we did that, we get 6 minus 1, which is 5. So f of 2 equals 5. And if we wanted to think of this as an ordered pair, our x value was 2, and our y value is now 5, because our input was 2, and our output was 5. Let's try another one. What about f of negative 3? F of negative 3 would be set up exactly the same way. F of negative 3 would be 3 times negative 3 minus 1. And if we did this math, 3 times negative 3 is negative 9, minus 1 is negative 10. And again, our value would be, our ordered pair would be negative 3, negative 10. Excuse me. We have 2 more here. What about f of 1/2? All right, well, it's just the same exact thing. So f of 1/2 is equal to 3 times 1/2 minus 1. Okay, so 3 times 1/2 is 1.5, minus 1 is 0.5, but let's just keep it as a fraction. So it's 1/2. So that means our ordered pair would be 1/2, comma, 1/2. All right, and the last one here is going to be a little bit of a tricky one. Our last one is f of x minus 2. Now, we're not going to get an ordered pair in this particular case, but if we want to do f of x minus 2, we have to do, okay, so let's plug in. We're essentially plugging in, rather than plugging in a number, we're going to plug in x minus 2. So we're going to say it's 3 times, using the same kind of notation we did before, x minus 2 minus 1. And then what you remember from your Algebra 1 is we have to distribute this 3. So this becomes a 3x, and then 3 times negative 2 is minus 6, minus 1. And we get a final answer here of 3x minus 6 minus 1 is a minus 7. So this would be our final answer of 3x minus 7. All right, so what that's going to do, that's going to conclude us, that's going to conclude this for us. So there's your first video. Congratulations. That's your first set of notes for Algebra 2. I hope they made sense. You will have your assignment sheet that you can work from. Good luck, and I will see you in class.